All right, just for absent people, this is what our warm-up looked like. We graphed this in our calculator. We looked at the table of values to graph the points, and we used the maximum and minimum functions on the calculator to find the y values of the maximums and minimums and then subtracted them. All right, exponential function. An exponential function, that's a surprise. An exponential function is a function in which the variable appears in the exponent. So like, for example, 2 to the x, that's exponential. X to the 2 is not exponential. What would x to the 2 be? It is squared. What's that kind of function called? We learned about it in this unit. Quadratic. Thanks, Sally. All right. So 2 to the x is exponential. X to the 2 is quadratic. All right, graphs. For the general exponential function, y equals, now notice this is just a general form, some constant k times some constant a to the x. X is the variable, plus c. Or you could have a negative x. Negative x reflects your graph across the y-axis. Plus c, of course. C controls the vertical position, so that's going to move it up and down. And the horizontal asymptote is at y equals c, because the whole graph is going to move up and down. That's going to move your horizontal asymptote as well. A and k both affect how steeply the graph increases or decreases. And the sign of k determines if it lies above or below the horizontal asymptote. So obviously positive would be above and negative would be below. Here it says to sketch the graph and then state the domain and the range of the function. So let's try this in our calculator. Go to your y equals and we'll clear it out. One thing the calculator doesn't show you is the asymptote. So after we get this in here, we'll consider what the parent function looks like. We have 2 raised to the negative x. On my calculator, I need to put parentheses around it, but you might not need to in yours. And then minus 3. Okay. So you get a different parent function depending on what base you have, but generally a parent function for y equals 2 to the x, 2 is the base right here, it's going to have a horizontal asymptote on the x-axis. So the parent function will have a horizontal asymptote on the x-axis. And then it's increasing. It goes through the point 0, 1. And it's increasing, approaching positive infinity on the right and approaching 0 on the left. Now this one you can see some things happen. First thing that you notice is that the asymptote is not at 0. It shifted down. And by looking at the equation, we can guess that it shifted down to what number? Negative 3. So draw a dashed line at at y equals negative 3. 1, 2, 3. These graphs are really hard on my eyes. If you see me get something totally off, just let me know. That looks like negative 3 though. All right, and then the rest of it we can get from the table of values. So just the table of values is not going to tell you where the asymptote is. So we can go to second table, and we're going to want some negative x values in addition to the positive ones. So I'm going to start back here at negative 3. And actually, I think I'm going to just make a little table of values over here so I can remember what points I graphed. Negative 3, negative 2, negative 1, 0, and 1 maybe. 5, 1. Negative 1, negative 2, and negative 2.5. So those are the points I'm going to graph. Oh boy, this is really hard on my eyes. 1, 2, 3. 1, 2, 3, 4, 5. Okay, I think that's right. And then negative 2, 1. Okay, and then you'll just sketch it in. Remember that you can get infinitely close to your horizontal asymptote, but you're not going to cross it with an exponential function. We have seen some rational functions that cross your horizontal asymptote, but the exponential function does not cross the horizontal asymptote. All right, so if you haven't yet, take a moment to find the domain and range of the function. I'm going to write it in two different notations just so that you get used to seeing that. 2. So the calculator does lie to you and tell you that you actually get to -3. Why is it telling you that you get to -3? It can't round that many decimal places, so it's really like 2.999999999, but when it's rounding to 3 decimal places, it just rounds to 3, okay? So remember that even though your calculator tells you -3, it doesn't get to -3. That means that your range starts with which one? Does it start with a parentheses or a square bracket? Yeah. So this parentheses means it doesn't really reach -3, even though your calculator is trying to make you believe that. And then it goes up to what? Infinity. All right, and then if you want to write that in set notation, it would look like this. I don't need you to know both ways. I just need you to be able to recognize both ways. All y such that y is greater than -3. Okay? If you can read that, you're good. How about the domain? What would the domain be? Yeah, -infinity to infinity. That's good. And then in set notation, all x such that x is an element of all real numbers. And this is fun to write. It's the R with the extra line, like that.
That's not fun, that's different.
Okay. All right, folks. This graph shows a curve, and they're telling you the format of it, and they're telling you that k and c are constants. So your variables are x and y, and they want you to find the values. All right, and the way we're going to do that is we are going to substitute the points that we have into the equation 2 times to get 2 equations in terms of k and c, and then we'll have 2 equations so we can solve them simultaneously. All right, so let's do that. This point I can see this is x and this is y. This 2, is that an x or a y? It's a y. Good. So this is the point 0, 2. So that's an x and that's a y. All right, so I'm going to substitute into this one. So I'll use this one first. It does not matter which one you do first. So I have 2 equals k times 3 to the x plus, 3 to the what? 3 to the 0, right? Plus c. What is 3 to the 0? Is 1. Anything to the 0 power is 1. So this is going to be 1k or just k. So 2 equals k plus c. All right, now I'm going to do the other point, this one. The y is -2, k times 3 to the 1 plus c. 3 to the 1 is what? 3. So I have -2 equals 3k plus c. So even though my equation is exponential, the system I end up here is just linear. Can you see that that's linear? There's no exponents in this at all. So I just have a linear system. If you know how to solve this system by hand, you can go ahead and solve it by hand. If you want to solve it on the calculator, you got to replace k and c with x and y to solve. I'm going to do both of those for you. I'm going to solve it by hand first. So I want to multiply this one by -1 so that I can cancel out my c's when I combine it with this one. So that would give me -2 equals -k minus c. multiplied by -1, so that now I can add these two equations together, and my c's will cancel. This will give me -4 equals 2k. And then this one divided by 2, I get k equals -2. So you can solve this by hand. Just because we have a calculator doesn't mean it's always the easiest way to do it. Now that's k, we need to find c. And I think I'll put it back into this original one, 2 equals k plus c. So remembering 2 equals k plus c, I'm going to put -2 for the k, so 2 equals -2 plus c, and add 2, and I get 4 equals c. So this is solving it by hand. I'm going to pause for a minute in case you want to process that, and then we'll do this on the calculator. All right, so to solve this by graphing, I would need to change k and c to x and y, which is confusing because there's an x and y in this problem, but it's okay. So let me just grab a corner over here to do that with, okay? So I have 2 equals k plus c. I'm going to write 2 equals x plus y. And then over here I have -2 equals 3k, so I'm going to write 3x plus y. So you'll notice that instead of k I have x, instead of c I have y, right? I need to solve these for y in order to graph them on my calculator. So this one becomes y equals 2 minus x, and this one becomes y equals -2 minus 3x. Now I'm going to graph these on the calculator and find the point of intersection. Oh, you guys should tell me that you couldn't see that because it was behind there. Here you go. So if you like the calculator method, you can also graph on the calculator. Y equals, and clear that out, 2 minus x. Oops, delete that one. And -2 minus 3x. And I'll graph that. And I need to find this point of intersection right here. You might be able to find it on your table. You can also find it with second, calculate, intersect. Enter, 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 and there it is. So x is -2, so that means that k is -2. And then y is 4, and so that means that c is 4. So x is -2, y is 4, which means k is -2, and c is 4. All right, what did you guys prefer? Did you prefer solving by hand or solving by graphing? What'd you like?
Could you just look at the graph and see that if it has the y-intercept, just be like, oh, it's 2 away, and it's reflected over the x-axis, so it's -2.
Say that one more time. It's
Well, the y-intercept is 2,
uh-huh.
and it's reflected, so that means.
So you were following the pattern?
Yeah.
Yeah, so if you can find that and you can convince me of your method, just remember you need to make your method clear on a test. Another way to find it, of course, is on the table. You can find where those values are matching up, right? So we could go back to -2. And then you can see that the y's are the same there. So that's the same point. But that will only work if it's an integer. If it's a decimal, you would definitely need to use the intersection. All right, questions before we go on? Okay. All right, I'm going to turn the page then. All right, exponential growth and decay. That's not really brand new because we talked about this a lot in our first unit. So if your base here is greater than 0, you're going to have growth because you keep multiplying by a number bigger than 0. Like, for example, if it's 2, multiplying by 2 is going to show you growth. If it is a number between 0 and 1, like, for example, 1/2, you'll have decay because every time you multiply by 1/2, you get smaller. And so if your a is a negative number, your graph is reflected, which means it's not growth or decay. Not every single graph is growth or decay. So you would not have an a value less than 0. All right, an entomologist monitoring the grasshopper plague notices that the area affected by the grasshoppers is given by this function, a of n equals 1,000 times 1.15 to the n hectares. I guess that's the way you measure area. I don't know what a hectare is. Does anybody else? All right, we're going to imagine it's the area, where n is the number of weeks after the initial observation. Find the original affected area. So the original affected area is how many weeks after the original observation? 0. Thank you. 0 weeks. Okay. So the original is when n equals 0. So we're going to put 0 into your function. 1,000 times 1.15 to the 0. All right, 1.15 to the 0 just gives us what? Just 1. Good. So 1,000 times 1 is just 1,000. So the area is going to be 1,000 hectares. Am I even saying that right? I don't imagine how else you could say it. So use that formula to find the affected area after 5 weeks and 10 weeks. Then I want you to draw a graph and then try part D. So I did tell you that you could round this to a whole number, so that would make this one 2,011 hectares. Make sure you put your unit on. Did you guys get 4,046 for the next one? Yeah. 4,046 hectares. All right, I'm going to zoom a little bit, but it's hard. I want to show you this. All right, so on your x-axis, consider counting by 2s, and on your y-axis, consider counting by thousands. And then you can use a table of values, but you have to put, obviously, the equation into your y equals. Why does my graph only have an arrow on the right side? Why is there no arrow on the left side? Yeah, it starts there. That's the initial observation. That's the first observation. So in the real world, often we don't have a negative side over here. We might not have a negative side over here. It just depends on what you're measuring and if that thing can be negative. All right, so you can go ahead and try part D if you know what to do. I'm going to give people a minute to catch up and then we'll talk about D. So that's the general shape of it. What you do want to practice being more exact and you should practice things. All right, so for part D, it says use your graph or technology to find out how long it will take for the affected area to reach 8,000 hectares. So would 8,000 be an x value or a y value on this graph? A y value. So you can just set y equal to that on the next line. So we want to know when the y is going to be 8,000. And we're going to probably have to change our window because right now I'm in a standard window, which does not go to 8,000, only goes to 10. So if I'm looking at the graph, I can't even see any of it. It's thinking still, but it's not going to let me see any of it. So I need to change my y. I think my x's are, well, I want my x's to go up to maybe more. So I'm just going to manually set my window. I'm going to set my x's to go up to, I'll say 100. I don't think I need that much. And then my y's, they have to go past 8,000, so I'm going to set them to 9,000. And I'll graph. All right, so there's my curve. I definitely did not need 100 on my x. And then my line should be coming. There's my line. And so I need to find this intersection right here. So I'll do second, calculate, intersect, which is 5. And I'm going to try enter, enter, enter. No, it didn't jump, did it? Oh, it did. Okay. So this is what I'm dealing with right here. So it's about 14.9 weeks. I went back to 3 sig figs there. About 14.9 weeks. If you worked ahead, you can check some of the answers here, but don't write them down if you didn't work ahead. It's really practicing the exact same thing right here. So we'll come back to that if we have time, but I really want to spend some time talking about logarithms today. So I'm going to go to the logarithm page, which is page 5. All right, everybody, let's please turn to the logarithm page. You should have phones away and be focused. So logarithms are both easier and harder than you think. Logarithms are easier than you think because people get confused because there's like a whole word in the middle of your equation. It's just the inverse of an exponential. Logarithms will undo your exponential. They're harder than you think because they have some really interesting properties that in Algebra 2 Regular, we didn't learn about those properties. So I'm going to show you today. They're in your formula book too. So if you have your formula book with you, take it out so you can see these properties of logarithms. We'll get to them shortly. We're going to go over the basics first though. All right, so the logarithmic function provides an alternate way to write exponential expressions, and it is in fact the inverse function of an exponential function. When you see a logarithm written log base b of a equals x, b is called the base. A is called the argument, but a lot of people just don't use a word for a. Argument. Does argument have an E in it after the U? I don't know. X is just the result. No? Okay. Thank you. I'll scratch it out. There you go. All right. If you have log base b of a equals x, that expression or that equation can be written as an exponential equation, b to the x equals a. This is something that we did learn in both Algebra 2 and Algebra 2 Honors, that you can take a logarithm and rewrite it as an exponential and vice versa. Sometimes one format will allow you to solve while the other one won't, so it's good to know how to translate between the two. Note that the base b has to be a positive number. So we can only find the log of a positive argument, and we can only talk about logs with a positive base. There are some special logs. There's one that is called the common log. And if you see it written as log of x, that means log with what base? Base 10, very good. So if you see log x, that means log base 10 of x. And that one's special because our whole number system is base 10, so we use that one a lot. The other special log is called natural log. And natural log is log base e. So if you see natural log, it's written as ln. I don't know why it's not ml, but it's ln. And that means ln of x means log base e of x. What's e? Does anybody know what e is? It's a number. E is a number.
Like pi, but for a different purpose. It's like never
Say it again?
Euler's number.
Yeah. He actually says his name Euler's number. It looks like Euler's number. Yeah. So it has a name, and it's a number just like pi is a number, right? Yeah. Sophia was reminding us that pi is an irrational number that goes on forever, just like e does. You should be able to find an e button on your calculator. Did anybody find it? It's like no, I is not real. E is real. It's just not rational. So here's an e to the x button. So let's do that. Let me do second quit, and then let me do second. Here's e to the x. I think there's just an e button too, but I'm going to do e to the first power. So here's an approximation of e. It's about 2.72. Just like pi is about 3.14, e is about 2.72. All right, but you get to use the e. You don't have to, or actually you'll use ln or you'll use e, so you don't have to know exactly what that number is. So we are going to evaluate by not using our calculator first. We're going to evaluate by changing these into exponential equations. So first one, log of 100. Now remember that means log base 10 of 100. And we're trying to find the answer to that, so we're going to put equals x. What does log base 10 of 100 equal? Why? Why is it 2? Right, because 10 to the second power, which is 10 times 10, equals 100. So when we rewrite this as an exponential, the base is 10. You write that first. The exponent is the result over here, so that would be x, and it equals 100. So the question is 10 to what power equals 100? And then again told it's as 2, so the answer is 2. So the answer to log base 10 of 100 equals x is 2. I want you to try part B here using the same method. Good. So the setup was log base 10 of 0.1 equals x, and then we had to rewrite that as 10 to the x equals 0.1. Can somebody read the number 0.1 to me? I didn't really read it correctly. How do you read that? 1 what? 1/10, right? Because it's in the tens place. So another way to think about this is x 10 to the x is equal to the fraction 1/10. And some of us are more used to seeing negative exponents written this way. Remember when you have x to the negative 1, it gives you the reciprocal of x to the 1. So 10 to the negative 1 would give you the reciprocal, which is 1/10. So that would be x equals -1. What would 10 to the negative 2 be? Try it. 10 to the negative 2 is going to give you 1 over what? 100. 1 over 10 squared, so 1 over 100? Yeah. Okay. All right. We are going to write these numbers as powers of 10. So that means that 10 to some number gives me 8. Now that would be a lot of guessing and checking, because I know that it's less than 1, because 10 to the 1 is 10. And I know it's greater than 0, because 10 to the 0 is 1. So it's some sort of decimal between 0 and 1, but I would be guessing and checking. So to avoid guessing and checking, we can rewrite this as a logarithm. So it would be log base what? Log base 10. And then comes the 8. And remember that we don't really write log base 10, we just write log. So there's a button on your calculator that says log. That means log base 10. And we're going to type log of 8 and find our answer. And I said, yeah, it says on this one to use 4 decimal places. So here's my log button, and I'm going to put 8. Yep, I think I get the same thing as Kaden, 0.9031. All right, so do B and C, please. You can obviously skip the step of writing log base 10 once you know that it's just going to go straight to log of 800. But it's good practice until you figure that out. Oh, and one thing I forgot is that it says to write it in the form 10 to the x. It doesn't just ask what x is. So this one we would write it as 10 to the 0.9031. Yeah, I have to pay attention and make sure I'm answering the question that's being asked. And then this one would be 10 to the 2.903. Oh, I'm missing it one, aren't I? What comes after the 3? Is it 1? Thanks. Negative 1.0969. Did you guys get that? Did you get that or something different? Okay. And then you're going to write it as 10 to the negative 1.0969. All right, so if you type log 2 and like log 20 in your calculator, for some reason we are now rounding to 3 decimal places, you should be able to get these answers. Log 2, you should get 0.301. And log 20, you should get 1.301. So the question in B is to explain why is log 20 exactly 1 more than log 2? And it has to do with these formulas that we haven't learned yet if you took regular Algebra 2. So we're going to go to your formula booklet and find them. Here they are. So I'm on page 5 of the formula booklet, and I'm looking at laws of logarithms. And if you don't have your formula booklet, remember you can get that in Course Essentials right here. So they're right up here. I think I can make them a little bit bigger. No, I cannot collapse that. Okay. All right, so looking at these and comparing it to part B there, which one do you think we might be applying? The first one, the second one, or the third one? Looking at part B, does that seem to relate more with the first, the second, or the third? Gonna compare it back. Notice I have addition between these two, right? Since I have addition, that would mean it's the first, the second, or the third? The first one. Okay, so look at this. It says if you have the sum of 2 logs with the same base, it can be rewritten as a single log of the product of those 2 things. Okay? If you have the sum of the log of 2 bases, it can be rewritten as the product of those 2 things. So we can rewrite, let's go back. We can rewrite 1 as log of what number? Log base 10 of what number gives us 1? That's a good question. Log base 10 of what number is going to equal 1? Let's try it. I heard 0 and I heard 10. 10 to the 1 equals, my question mark was 10 to the 1? 10. So we're going to write this, the 1 as the log of 10. Okay, so this is the same as log 10. Plus log 2. Okay, so we have log 2 plus log 10. Now, if we go back and we look at our formula booklet, if I have two logarithms with the same base, I can rewrite that as the log of their products, and 2 times 10 is 20. So for some people, this is a surprising property for logarithms. It is related to the property of exponents that says when you multiply two powers with the same base, you add their exponents. But it's not exactly the same thing, right? Because it's an inverse, it does work inversely. So it says if you have two logarithms with the same base, you can do the logarithm of the products of the, what are these? The arguments. And it's going to give you log 20. All right, so I am going to suggest that you spend some time looking over these and considering how those might apply, because there's not a whole lot of applications in these notes. All right, let's turn the page. Let's do our last page of logarithms. We have an earthquake example. Logarithms always have an earthquake example. Put it past them. All right. The magnitude of an earthquake which releases E joules of energy is given by this equation. Find the magnitude of an earthquake which releases 5.1 times 10 to the 10th joules of energy. So we're going to put that number for energy and we're going to evaluate it, okay? So that simply goes for your E. Okay, be careful entering that in your calculator, but it is a simple calculator problem. So let's see what you get. All right, so here's what Maher was telling us about. Euler's number E is named after the mathematician Leonhard Euler, which I don't believe did have a lowercase e. That's very modern. And it's a famous irrational number. And we call the function y equals e to the x the exponential function to distinguish it from what? How does that distinguish it from all other exponential functions? I will get that information for you. But natural logarithms are logs with base e. Natural logarithms are logs with base e. So if you think about it, y is equal to e to the x. That would be written as log base e of y equals x. But we don't write log base e. Instead, we write ln. Okay? So even though I would understand what you meant if you wrote log base e, it's just proper to write ln instead of log base e. And ln of e to the x, those are inverse functions, so they cancel out. So if I do ln of e to the x, those two cancel and give me just x. Or if I do e raised to the ln x, those two cancel and just give me x. They're inverses. So skipping over A for a moment, I could do a problem like this one, B, by rewriting this as ln e to what exponent? Yes. Sure, put it past in. ln e to what, e to what exponent, guys? -4, good. Okay, then the ln and the e cancel, and I just get -4. So ln and e are inverse functions. ln and e to the x are inverse functions. So what's the answer to A? 3. Now, unfortunately, in C, that 2 is in the way of us applying that inverse property. That 2 is just in the way. We have to move that 2. And there is a way to move that 2. What we're going to do for a moment is ignore the E. Just look at 2ln5 for a moment, okay? And even thought bubble this. 2ln5. Okay? I need to go back to your formula booklet. So back in your formula booklet, there is this one with exponents. It's the third one right here. You see it? This one. It says that if you have an exponent here, you can actually move that exponent to the front of your logarithm. And that's what I have. See how I have a 2 right here in front of my logarithm. What I'm going to do is I'm going to take that 2 and it can become an exponent on the x right here. Okay, so this is another property of logarithms. It just says these two things are equal to each other. So going back over here, this 2 can become an exponent on the 5. So 2ln5 is equal to the ln of 5 squared. And it's weird, and it seems like maybe that's unlikely, but you can type them into your calculator and you will find it is true. So I'm going to rewrite this as e raised to the ln of 5 squared. And then I can cancel out the e and the ln, and 5 squared gives me what? 25. So I feel like things like that would be really good things to practice in that last math space, even though a lot of you don't have to do that last math space because you already did 2 math spaces and you're going to do an IB questions. I'm suggesting that you do extra so that you don't do less well on your third topic than you did on the first 2. Go ahead.
How did you toss it out?
Okay, so you're okay with 2ln5 becoming ln5 squared? That one came from the properties of logarithms that are in your formula booklet. So it says if you have a number in front of your logarithm, like a coefficient, that can become an exponent on your argument here. Okay? So, but you were asking me about the second step. All right, so e to the x and natural log, which is log base e, those are inverse functions, and inverse functions undo each other. So the effect of e to the x and the ln cancel out, leaving you with only this 5 squared. That's it. So notice we did that here too. ln and e canceled out, so we just get 3 for this one. Okay. All right, use your calculator to write the following in terms of e to the k, where k is correct to 4 decimal places. So we're going to write e to the k equals 50. And then what function will undo e? ln. Good. So what we're going to do next is we're going to take the natural log of each side. So ln of e to the k equals ln of 50. And those cancel out. So to find k, I just need to use my calculator to do ln 50. Okay, and it says 4 decimal places, so I'm getting 3.9120. And so I'm going to write it as e to the 3.9120. If I type that in my calculator, it should give me a number that rounds to 50, very close to 50. All right, do the last one with the same method. All right, negative 5.2983. Okay, so just going back to the page that we skipped over, when a diesel electric generator is switched off, the current dies away according to this formula. T is the time in seconds after the power is cut. So to find the value when T is 0, 1, 2, 3, you simply substitute that for the T. So you'll use your calculator, 24 times 0.25 to the 0, and you'll get 24. And you'll do the same for these values here. What amount of current flowed when the instant it was shut off? That's when time is 0, when it was shut off. So you should get 24 and write 24 amps to add your unit. And then you're just going to make a graph of these numbers here. So 0, 24, 1, 6, 2, 1.5, and 3, 0.375. That's definitely going to be an estimate. You do your best there. And you're going to graph the function. And then lastly, it says use your graph or technology to find out how long it takes for the current to reach 4 amps. So in your y1, you'll put the function. In your y2, you'll put 4. You'll get two functions. You'll get the exponential and a line. And you'll go to second and calculate, which is above trace, and intersect, enter, enter, enter. And you should get that the answer is about 1.29 seconds.